Okay, we've got a triple integral from 0 to 1, 0 to x, and 0 to x minus y. Notice they've given you the order dz, dy, dx. So we have 2x plus 3y dz, dy, dx. This tells us you need to integrate this expression with respect to z first. Easy enough to do. That becomes 2xz plus 3yz. Then we plug in x minus y, plug in 0, and find the difference. When I do this, I get 2x squared minus 2xy plus 3xy minus 3y squared, minus what I get when I plug in 0. But when I plug in 0 for z, I get 0. Now I integrate this result from 0 to x. So I have the integral of 2x squared minus 2. Well, let's say this. Let's say negative 2xy plus 3xy. That will combine to make plus xy. And then I have minus 3y squared dy, which we're evaluating from 0 to x. This is going to give us 2x squared y plus xy squared over 2. This marker is squeaking too much. It's killing me. Minus y cubed, plug in x, plug in 0, find the difference. And this gives me 2x cubed plus x cubed over 2 minus x cubed, minus what I get when I plug in 0. When I plug in 0, I get 0. And then I integrate this from 0 to 1. So I have the integral of, I'm going to combine these terms. This is x cubed, but then plus x cubed over 2 gives me 3/2 x cubed from 0 to 1. That's 3/8 x to the 4th. Plug in 1, plug in 0, find the difference, and you should get 3/8, assuming I haven't screwed that up. Looks like an answer to me. Is that good?
Yes.
Okay. Do you want to do the next triple integral? It's very similar.
Is there any tricky part to it?
Nope.
Then let's skip
Can
it.
Wolfram do this in one step?
Yes.
You can just type in.
No. There's a widget for it. Probably it's something called a triple integral widget you have to look up.
Okay.
Okay. We're going to skip to 3 because 3 is different than number. 2 is very identical, almost identical to number 1 in terms of the process. Number 3 is harder because they don't give you the bounds in place. So if the bounds are already on the integral, great, super easy. Like I don't have to think about how I construct the bounds. When the bounds are not given, or the bounds are not put on the integral, and I have some region over which I'm integrating, well then I have to figure out what bounds I'm integrating over. That's the harder problem to do. So this one we have the triple integral of 3x. Sure, it says dx, dy, dz, but you can do whatever order you want. I actually don't even like the notation dx, dy, dz unless they've already got bounds in place, but they don't have bounds in place. So they really should say dv. D capital V indicates that there's no specific order that you have to do this under. Whatever order you want to do works, as long as it's easy to do. The fact that they've already put dx, dy, dz there makes you think that you have to do dx first, but you don't. So unless the bounds are already in place, as they were in problems 1 and 2, where the bounds are already on the integral, you must do the order they give you. But in this case, are there bounds already on the integrals? No, and so there's no reason to have to do the dx, dy, dz. So what order would I prefer to do? Well, I am told that x goes from 0 to square root of 4 minus y squared. I'm also told that z goes from 0 to y, and y goes from z to 2. Let's do, we'll do x last. Actually, we'll do x first. And then we'll do, let's say, dz, dy. Okay? It doesn't really matter. You might find that sometimes you're going to guess wrong and it's going to come out to be something ugly or undoable, or it's going to require a technique of integration that's going to hurt. And we want to try and avoid doing crazy techniques of integration. So I'm going to try dz or dx, dz, dy first. Hope it works out. What are my bounds for x?
0 to square root of 4 minus y squared.
Right. What are my bounds on z? Now, careful, this one's tricky. You have this compound inequality involving both z and y. When you're doing this middle integral, you take z's bounds to be whatever variable bounds it has immediately. So the lowest value for z is what?
0.
But then the variable bound, upper bound is what?
Y.
Y. And then what are the bounds on y?
Z to 2.
No.
0 to 2.
Yes, the outermost bounds are always what? I said this last week.
Constants.
Are always constants. So In this case, y goes from the lowest value constant 0 to its highest value constant 2. Now we just integrate. The integral of 3x with respect to x is 3x. At this point, it's just pretty simple integration, which I probably shouldn't even waste my time doing this, but whatever, I'm already here.
Wait, can we just skip it?
Nope. I can't help myself. Integrating with
math
respect to z, 0 to y, gives me 3 halves. Let's do this. I get 6y minus 3 halves y cubed. Integrate this from 0 to 2. And I get 3y squared minus 3/8 y to the 4th. Plug in 0, plug in 2, find the difference. I get 12 minus 6, which is 6. That's an answer. Is it right?
3y squared minus 3/8 y to the 4th.
Plug in 2 squared is 4 times 3 is 12. 2 to the 4th is 16 divided by 8 is 2 times 3 is 6. 12 minus 6 is 6.
Yeah, you're good.
Okay. 4 is, I wonder if they want you to convert this to spherical. Let me think for a second. So whether or not they want you to convert this to spherical coordinates is irrelevant. I'm going to teach you how to do this using spherical coordinates because it's something you probably should get under your belt sooner than later. To say nothing of the fact, yeah, actually, you know what? If you try to integrate this first with respect to z, you're going to come up with a nightmare. 5xy. Yeah, let's just talk about how we have to talk about this problem. Okay. There's 2 ways they want you to do this problem, and I'm going to show you the one that's better. But let's start with the fact that, was it 0 to 1, 0 to square root of 1 minus x squared, and then 0 to square root of 1 minus x squared minus y squared? Yes?
Yeah.
Yes. Yes.
If you preserve this order, you're going to run into some problems. If I first integrate this guy with respect to z, I'm going to end up with 5xy square root of 1 minus x squared minus y squared. And I guess I could do a u sub on this. When I integrate this with respect to y, I would go ahead and say something that like u equals 1 minus x squared minus y squared. And so du would equal negative 2y dy. And then I do a u sub on that. And I get a result from there, and then I integrate that result with respect. Yeah, that would work, but it's already pretty gross, right? And I would like to avoid trying to do that if at all possible. One thing you can do to make your life a little easier is change the order of integration. So the region in question is this shape here. Let me get a different color. You should know what this shape looks like. What is z equals the square root of 1 minus x squared minus y squared? Or if I were to rearrange this and write this as x squared plus y squared plus z squared equals 1. What is this the equation of?
An ellipse?
Warm, but not quite right. Ellipse is something where you have x squared and y squared, and you have differing coefficients of x squared and y squared. What if it was just this? What is x squared plus y squared equals 1?
Sphere.
Oh.
Yes, someone who just, I think Brandy, you said sphere, yes?
Yeah.
This is a sphere, okay? Sphere of radius 1, center of the origin. So this is the upper hemisphere. And then the bounds over here indicate that actually we want the right semicircle, and basically we only want the first octant hemisphere, or I don't know what you would say, 1/8 of a sphere. Basically, the whole sphere goes this way and back that way and down underneath, but we only want that part which exists in the first octant where x, y, and z are all positive. Rather than integrate from 0 to square root of 1 minus x squared minus y squared, we could opt to do this. We could say, all right, I'm going to change the order up and say I'm going to do the triple integral from 0 to 1, 0 to square root of 1 minus y squared, and then I'll say 0 to the square root of 1 minus x squared, 1 minus y squared minus z squared. Is this going to be any better, actually? Yeah, this will be slightly better because why is this better? When you go to integrate this guy with respect to x first, now then we have dz dy, what's the integral of 5xy with respect to x?
Hold on. Wait, what's the integral of 5xy?
Don't write this down. This is not going to be this is probably not going to be the way we do this. What's the integral of this guy with respect to 5xy with respect to x?
5x squared y over 2.
Right. And the reason this is nice is because when I go to plug in my upper bound of 1 minus the square root, or square root of 1 minus y squared minus z squared, what happens to that square root?
Goes away.
goes away by virtue of squaring the x, right? That didn't happen up here because when you integrated 5xy with respect to z, you didn't get a z squared, you just got a plain old z. And then when you don't end up squaring the square root. So you get stuck with this square root here. You don't have that happen here because you're squaring the x. So you see why it's advantageous here to switch from the order that was given to us to an order that has us squaring either the x or the y. Hopefully you see that, right?
Yeah, I see it.
yeah.
But I thought you said you couldn't switch the bounds if the bounds are given or something like that.
If the bounds are given in place, you can't change this order around willy-nilly, but you can change this order around as long as you change the bounds around, right? Which I did, right? And instead of doing the order dz, dy, dx, I have to do dx, dy, dx, dz, dy. So my bounds for x went from 0 to square root of 1 minus y squared minus z squared, as opposed to 0 to square root of 1 minus x squared minus y squared. But I'll say this. This method is, I think, a little bit harder than the method I'm about to show you, which uses spherical coordinates, okay? So let me show you how spherical coordinates works. So spherical coordinates works like this. We remember that x equals, we'll see if I regret this or not. I'm not sure, because maybe this doesn't come out to be as nice as I want it to. X equals rho cosine theta sine phi, right? You guys remember that from exam 1?
Yeah.
Yes.
Just say yes. Good.
Yes, I do remember.
Okay. Those are what we're going to sub into 5x and y. Let's go ahead and do that now. This is going to be 5 times rho cosine theta sine phi times rho sine theta sine phi. But there's one additional change you need to make. That when you convert over to spherical coordinates in an integral, you have to introduce what's called the Jacobian for spherical coordinates. And that is, let me do this in blue, rho squared sine phi d rho d phi d theta. So this is a conversion from Cartesian, dx, dy, dz, or whatever order you want for Cartesian, to spherical. When you do spherical, you must throw in this rho squared sine phi term, okay? Now, what about our bounds on rho, phi, and theta? Well, this is a sphere of what radius?
1.
Yeah, you kind of put your pencil or your marker or whatever, your pen at the origin, and you draw outward until you hit the outer shell of the region. In this case, the outer shell of the region is a constant 1, right? The distance from the origin to this edge is always 1. It would be a different function if it wasn't a constant, but it is a constant 1. So our bounds for rho go from 0 to 1. What are our bounds for phi? Oh, actually, let's do our bounds for theta. If you were to look at a top-down view of this is your positive x-axis, this is your positive y-axis. And remember, we're only dealing with the first octant here. What are our bounds on theta going to be?
0 to pi over 2.
Yeah, 0 to pi over 2. 0 to 2 pi would be the whole thing, but remember, we're only getting 0 to pi over 2 here. Okay, if I wanted the whole hemisphere all the way around, I'd say 0 to 2 pi. And lastly, what about my bounds on phi? So you might not remember how phi is defined. Phi is defined to be, think about the globe. It might help to think about the Earth, okay? The North Pole, where Santa is, North Pole is 0 degrees or 0 radians, okay? And then the South Pole is 180, or we'll say pi, okay? And then as you kind of go downward, down your latitude, that increases your value of theta. In fact, how many degrees is it from the North Pole to the equator?
90.
I'll put it this way. If we know the North Pole is 0 degrees, and we know the South Pole is 180 degrees, or pi radians, what's the equator?
90.
90, or pi over 2, right? So in our case, we are going from, here's the North Pole, we are going down our sphere, down toward the XY plane, and then we stop. We don't ever dip below the XY plane. We never dip below the equator. With that in mind, our bounds on phi go from where to where?
0 to pi over 2.
Yep. What does this integral have now as its bounds that are advantageous compared to the previous integral we had? The bounds are all what here? Anyone?
Hold on. What did you say? It broke up.
Yeah. What advantages does this integral give us? The bounds are all what?
In radians?
I don't care about the radians. I don't care about
their positions on the unit.
Compare them to these integrals. Look at the bounds here and look at the bounds here.
There's no variables.
AKA they're what?
Constants.
Constant.
I said constants 3 times and you didn't respond.
I couldn't hear you. Sorry, bud. Yeah, they're constants. They're no variables. So I don't know why it didn't come through. Usually the call quality is usually pretty good. But yeah, they are constants. What we want to do is I'm going to multiply this out, though. Actually, I'm going to give you a trick you can use that might make your integration a bit easier. I'll say this. This is a super cool trick you can use to make integration a little bit simpler. If the bounds are all constants and the function that you integrate is a product of functions of the variables in question, then you can split the integral up into a product of 3 integrals. Let me repeat that. If the bounds are all constants and the function can be written as some function of rho times some function of theta times some function of phi, and this is true for any integral system or coordinate system, it doesn't have to be spherical. But if the function can be written as a product of one function of rho, one function of theta, and one function of phi, you can do each individual integral separately. So for instance, I can do this rho cubed d rho, and I can say, oh, that's 0 to 1, not 0 to pi over 2. Be careful. Damn it. My bounds on theta go from 0 to pi over 2. And my functions involving theta are cosine theta and sine theta. So I have sine theta, cosine theta. And then I have times integral from 0 to pi over 2. What ends up being sine, sine, and sine. So sine cubed. Oh, no, this would be a rho to the 4th, wouldn't it? There's a rho here, and a rho squared here. So that'd be a rho to the 4th. And we have a sine cubed of phi here. Now you might be looking at this and say, wow, is this really that much simpler? I mean, there really isn't an easy way to do this problem. Except there were 3 options here, and I'll label them. Option 1 has you doing this integral as was presented to you. And if you do that, you end up with this weird square root term that you then have to do some sort of crazy u substitution for. Okay, that's fine. You could do that, and actually you might end up having to do another u substitution when you go to do the dy integral. So I don't think this way is the best. The second way might seem the best, but it requires knowledge of how you rewrite this using a different order of integration. Rather than doing dz dy dx, you do dx dy dz dy, and then what happens? What's the advantage of this method? Well, when you integrate 5xy with respect to x, you get a 5x squared y over 2, and the benefit of that squared is that what happens to the square root? Hello?
Huh?
Goes away. Goes away.
Goes away. The benefit of this using this method is while you do have to do the mental energy, expend the mental energy to figure out how the bounds are rewritten, you at least can get the square root to go away by squaring it when you integrate the 5xy over 2 with respect to x. And that might be the best way right now. The other way is to convert everything to spherical. Now, this might be ahead of its time in terms of what homework you're on, but you will have to know this anyway, so I might as well just get it out of the way. So converting to spherical, and this makes sense. Why would I convert to spherical? Well, what shape is the region we're integrating over?
Sphere.
The sphere, so we might as well use spherical, right? We convert all the x's and y's over to rhos, phis, and thetas. You have to have this conversion factor of rho squared sine phi d rho d phi d theta, and then you just integrate all the way through. And the advantages of this are all the bounds are constants. I don't have to worry about extra variables or the order being switched around because of the different variables. All the bounds are constants, and so I can just integrate with these. This is going to give me 1/5 if you do this integral. This is going to give me 1/2 if you do this integral. Just trust me, I'm doing this in my head. This is going to give me 2/3, I think. Negative cosine theta plus cosine cubed theta over 2, over 3 rather. So it's going to be -1. I think that's right. Okay. And then if I plug in 0, I get -1 plus 1/3, which is -2/3, but it's plus it's 2/3. So this comes out to be, when you do all this integration, you get 1/2 times 1/5, which is 1/10 times 2/3, which is 1/15. Not even an answer. Oh, there's a times of 5 at the very beginning. I was worried about that. I was going to say. So 5 times 1/5 is 1, times 1/2 times 2/3 is 1/3. 1/3 is an answer, right?
I believe so.
Try it. See if we're right.
Mine should be 2/5, which is
Yep.
They're right.
Yep.
So this problem sucks for sure. Like,
good question.
what's up? Yeah.
So what if in like the original problem, the bound, like, is it always going to be a sphere?
No.
'Cause this one was really obvious because it's square root 1 minus
Yeah,
x
right.
squared.
That doesn't. It doesn't have to be a sphere. It could be a rectangular prism. It could be any sort of other weird function. It could be a plane.
Spherical?
What's up?
But then you can't do spherical method, or you
Correct.
still
Or at least you wouldn't want to, right? Like, what is you have to think back to when you had Calc 2. The only reason you'd ever convert a double integral to polar, and you might remember using polar when we had to convert dA to r dr d theta. Does that sound familiar? R dr d theta? Maybe a little bit.
Yeah.
The polar conversion from Cartesian to a polar with the r dr d theta. We only wanted to do this if the region that we were integrating over was what shape in nature was what shape.
circle.
Something circular, right? Holy cow, I can't talk today. Yeah, something circular is what lended itself to being done using polar. Cool. And so to answer your question, in the same fashion, we should only really want to convert over to spherical coordinates if the region we're integrating over is something spherical. Good?
Yeah.
Okay. I think we're done with 4. We're going to move on.
My question was no bueno.
Yeah, no, not at all. Getting an error on loading the picture, so hold on. There we go. Okay. Oh, okay. This is just like, what would you see if you saw it projected in the XY plane? You can kind of see, oh well, I have to erase this. You can kind of see, if you were to look at a top-down view of the picture that's given, what shape would you see? Or just look at the shape that this guy makes with the XY plane.
Triangle?
Yeah. And it's a triangle where one leg hugs which axis? The x-axis or the y-axis?
The X.
Yep. And so with that in mind, choose that answer, right? We're looking for a triangle that hugs the...
Wait, how do you know it's a triangle? Just looking from above?
Well, look at where this shape intersects the XY plane. What shape does that make?
Triangle.
Right? That's it.
Yeah, that was easy. That was right. That was the answer.
Now I want to let me mix it up and say, what if they asked for the projection into the XZ plane? What is this shape's projection in the XZ plane? Well, if you were to see what it looks like in the XZ plane, like what intersection is that making with the XZ plane? What shape would you say it's making?
Like
a quarter of a circle?
yeah.
No.
It'd be like hugging the X, hugging the Z with like a curved line between X and Z.
Are you guys seeing that?
Yeah.
That's not, well, that's more of a what than a circle. I mean, I don't blame you because you didn't really see the function. You can, but you know what? You can see the function literally underneath the you can see the name of the or how the function is defined underneath the picture. I wouldn't say circle. I would say what?
Cylinder? What?
Don't say cylinder. Look at the equation.
Sphere.
Yeah. Okay. Z equals 1 minus x squared. That's the equation of A. Guys. A sphere, not a circle. Nothing. We got nothing on this one. Okay. Let me help you out. What's that shape called?
Square?
This is a square.
Gold. Yes, we know. Andy, we know.
What's it called? You know a word.
Parabola.
Thank you. Why haven't you said parabola this entire time?
Oh, that's the word you're looking for.
Yeah, it's just a parabola. You said like a circle or a quarter circle or something.
That's half a parabola.
Sure, half a parabola would have been fine, but if you would at least said parabola instead of circle, right? Or square.
Can I say parabola?
That would be fine. That is better than semicircle or circle. Okay.
Paraboloid.
That's fine. Yeah. Okay. Just bear in mind that you could be asked some, or use the integral, use your part one, write the triple integral. Okay. They're opting to do dz, dy, dx. So we didn't actually do this too much when we did double integrals, but we have to do it with triple. So here's how this works. I wish I had drawn it differently than that. I'm gonna try and replicate what you're seeing.
Wait, are we on 6?
Yes.
Oh shit. That's fine. Okay. The order, looking at answer choice 6, or looking at question 6, what order are they asking us to integrate with respect to? What variable are they asking us to integrate with respect to first?
Z.
Z. As you draw a line parallel to the z-axis from underneath the region, what do you first hit when you enter the region?
The XY plane.
XY plane. So our lower bound for z would be what?
0.
0. That's the XY plane. Good job, buddy. Okay. Keep going up. What do we hit when we leave the region?
The radius.
So again, you say radius as if it's a circle. It's not a circle. But what's the equation of this shape here? They tell us it's what?
Parabola.
They tell us the equation of the shape, which is what?
Z equals 1 minus x squared.
So what's your upper bound?
1 minus x squared.
1 minus x squared.
Right. As I draw a line parallel to the z-axis, the first thing I hit when I enter the region is z equals what?
0.
Then I continue through the region and I hit what region or what shape or what boundary when I leave?
Squared.
Z equals 1 minus x squared. Good. Okay, now we're going to move on to our bounds for x and y. What order do they want next? So they want dz, then they want dy next. So let's.
Oh, they want dy. Wait, they want. Oh yeah, dz. Yeah, never mind. Sorry.
Let's look at. So this is dz, dy, dx. Let's draw the picture that we got from our answer to part 1, which was this triangle, right? That was our answer to the previous question. Yes. As I draw a line, so I'm doing dy now. dy says, as I draw a line parallel to the y-axis, what do I hit first when I enter the region?
0.
0. What do I hit when I leave the region?
X.
Yeah. What is the equation of this line?
X.
That's not an equation.
Y equals x.
Y equals mx plus b, which is 0.
Well,
Y equals x.
there's y equals x is the equation of this line, right? So y equals x. So yes, you do hit x, but I want to make sure you're saying, here's why this matters. Because if I opt to integrate first with respect to x rather than respect to y, what would I hit when I enter the region going from left to right? I would hit what?
X.
You won't say x, and this is my point, right? If you integrate first with respect to x, you don't hit x, you hit
y.
You hit y. You can't say the variable that you're integrating with respect to. So when I integrate first with respect to y, I hit 0, then I hit x. If I integrate this direction first, if I do dx dy, the first thing I hit is what?
Y.
Y, and then I hit 1, right? Okay, what are my bounds for, now that I've done that, what are my bounds for x? What's the leftmost value of x?
0.
0. What's the rightmost value of x?
1.
1. Hopefully you weren't tempted to say y to 1, because again, the outermost bounds are always what?
Constant.
Constants. Good. Okay, with that in mind, you should have an answer that matches something on Quest. Something like answer choice 3 for me.
Yeah, I got it.
Use your answer to part 2 to evaluate the triple integral. At this point, you're done, because, or I'm not going to do this one because it's just like the questions 1 and 2. The function in this question is 2x plus y. You integrate this with respect to z from 0 to 1 minus x squared. Plug in 1 minus x squared, plug in 0, find the difference. Then you do the same thing for y and x. Is that good?
Wait, can you say that again?
You have the setup. Can you do this integral?
All right, next.
Okay, I was going to say. Oh, I hate this. Jacobian.
Hold on, wait. Let me get there. Oh, this one's the long one. Damn.
10 questions? Come on. Come on.
Is it 10?
Yeah. Half the stuff isn't even on the test, is the funny part.
So this is what's called your Jacobian. Go ahead and rattle off these for this particular problem. What are the partial derivatives for me, or at least look in your partial derivatives?
Wait, for what?
Problem number 1. You've got two functions of x, one function of x of u, one function called x, which is in terms of u and v, another function called y, which is also in terms of u and v. And you need to compute these partial derivatives for me so that you can compute your Jacobian, which are, what's your partial of x with respect to u?
1.
Good. Partial with respect to v?
With respect to v, 2.
Good job. Partial of y with respect to u?
1.
And then?
4.
Cool. Can you take this determinant? Do you know how to take a 2 by 2 determinant?
Wait, hold on. Sorry, I'm not looking at your screen. My bad. I wasn't looking. I was like looking at the quest, trying to set this up. Yes, I know how to take that. Just give me a second.
All right.
2.
Good job. 1 times 4 is 4, minus 2 times 1, that's just 2. That's your Jacobian. That's your answer.
Okay, wait, hold on. I need to write down that thing on top.
Not really. You don't.
I won't know where I got all these numbers from.
Well, let's put it this way. How many variables are there?
2.
Well, there's 2 for x, the x and y, and there's the u and v, right?
Yes.
Okay. In the upper left corner, you put the partial of the first variable in the original coordinate system with respect to the variable in the second coordinate system.
I see.
And then in the bottom right, you put the partial derivative of the second variable in the first coordinate system with respect to the second variable in the second coordinate system. Now you might say, well, how do I know which one goes where for this? Well, guess what?
What?
Doesn't matter, right?
It doesn't matter.
Right, because when you do these determinants, you do minus this times this. But if you would swap these two, it wouldn't make a difference, right? Now, technically, it might mean something in terms of when you guys had Beckner for differential equations and you had to plot phase portrait diagrams and stuff like that, the order probably did matter, but for this class, it doesn't. We don't really, as long as you're saying, I need to take the partial derivative of the first variable with respect to the second and the other, and then take the partial of the second variable with respect to the first and the other coordinate system. Doesn't matter where I put them here as long as I do one of each on the off diagonal. Okay, number 2. Very similar. It's just going to be a pain in the ass to take these partial derivatives because you're probably going to need quotient rule and some sort of mess like that. So you guys want to do this, or can you?
Both correct.
Okay, yeah, sure. If you want to take the thing is, yeah, I guess it's reasonable.
Wait. What'd you say? Hold on. It keeps on. Why is my thing so bad? What did you say? Say it again.
You need to take these partial derivatives with respect to u and v, and they might require quotient rule, especially because we have u and v present in both the numerator and the denominator in certain instances, right? So if I ask you to take the derivative of x with respect to u, what would you tell me? What is the derivative of u over 3u plus 4v?
Quotient rule.
Yeah, what is the derivative? I'm not asking how you would do it.
You're asking me for it?
Let's just go to the next.
Oh, okay. Just go to the next one. Okay.
Or it's just going to take time to do it. Why take time?
All right, this one shouldn't take as much time. What's the partial derivative of x with respect to u?
Are we actually doing this?
Yep.
Yeah.
This one's faster. There's no quotient rule. You can do this.
Wait, what number is this?
Bruh.
3. Number 3.
Gee, stop complaining.
Yeah, 3.
The derivative of x with respect to u?
Yeah.
3 sine v.
Oh, hey, not that bad. See? What's the partial derivative of it with respect to v?
Of that with respect to v? 3
Not this, of the original.
3u cosine v.
Yeah. Okay. Partial derivative of y with respect to u?
Sorry. Partial derivative of y with respect to u. 4 cosine v.
And the partial derivative of that with respect to v?
4u, or negative 4u sine v.
Good. Okay, let's multiply. This times this is negative 12 u sine squared. And then we have minus 12 u cosine squared. What can I factor out of this expression?
Negative 12u.
Good. And if I do that, I get negative 12u times sine squared v plus cosine squared v.
1.
That's just 1, right? So I just get negative 12u. Damn. Yeah, okay. So the order doesn't, well, it wouldn't matter. Again, it wouldn't matter. So I get negative 12u. Now, I'm curious to know, is negative 12u right, or are they just want?
Yeah, that's right.
Okay, for the purposes of doing a double integral, I think you take the absolute value of this. Like, you're never supposed to have a negative here. So it's weird that we got a negative here, but we're not actually computing a double integral, but I guess it won't matter just yet. Okay, number 4. 4 is almost identical. Do you want to do that one?
Number 4? Yeah, let's fucking do it. Why not?
What is the partial derivative of
No,
two-
no.
Be quiet. While
My
we're sitting
answers
there,
are
might as
different,
well
so
just
it's
do it.
taking longer.
I hear two people at the same time. What's going on?
Don't listen to him. Don't listen to him. Keep going.
Okay, well, you're going to keep going. What's the partial derivative of 2e to the r sine theta with respect to r?
With respect to r, at just 2er sine theta.
Yep. Partial with respect to theta?
2er cosine theta.
Good. Now the partial of the second guy with respect to r.
Sorry. Negative 3e negative r, whatever it is, cosine theta.
Yeah.
And then with respect to theta is negative 3e to the negative r sine theta.
Yep.
Multiply. We're left with what? Negative 6 sine squared theta.
Yep.
Yeah. Plus 6, yeah, because the e. Yeah. Just half angle. What is this law?
The double angle formula. So you got to know these way back from pre-calc. Sine 2 theta is 2 sine theta cosine theta.
See, this is why we do these, Chi. Okay.
Good. You got to know these double angle formulas because they're going to crop up.
Let me write those down.
And there are obvious alternatives for these. I could use the Pythagorean identity to rewrite each of these individual sine squares and cosine squares. So this is equivalent to 1 minus 2 sine squared theta. It's also equivalent to 2 cosine squared theta minus 1. So be wary of that. All right. So number 5. All right. We good on this?
Yes.
I'm going to keep this determinant form up here because we might revisit it later. But we're now going to do a double integral using polar coordinates. And again, the reason we do why would we use a polar coordinate transformation? Because the region is what shape? The region we're integrating over, I should say.
Wait, sorry, hold on. Okay, say that again. I was submitting my answer.
We're doing a polar coordinate transformation on this. And why are we doing that? Because the region we're integrating over is what shape?
No, I accidentally just clicked. I thought that I just answered number 5, but really I'd answered number 4.
Did you get it right anywhere? Did you luck out?
Yeah, and I still got it right. Number 5 is 98 over 3 pi, but
Yeah, we're going to do it anyway. Okay,
let's
so
do it anyways.
our region of integration is what shape?
Circle.
Yeah, where do you see that as a circle? Where does it say that it's a circle?
X squared plus y squared between 2 different radiuses. That's how we can tell.
So really, it's more a circle's not wrong. You're kind of right, but really, it's between 2 different radii, right? So it's more of it's less a circle and more of a what?
I'm not sure what you're getting at.
Like the circle with a hole in it? No.
Yeah, we'll call it a ring. How about that?
Ring.
Or a washer. Some people call it a washer. Okay, so it's got this shape.
Donut.
Donut, sure.
You like that? Big donuts? Is that how we have to teach you using food?
Yeah. A donut usually implies 3 dimensions, though. So that would be a torus, like so here's what's interesting.
I'm actually a Sagittarius.
That's a good joke. That's a really good joke. I gotta use that.
Are you gonna write that down on your pad?
That's actually good. So a circle is to a sphere the same way a washer is to a what? You say donut, but the technical math term is what? Where you made your punchline, your joke?
Torus or whatever.
Torus. It's a torus, right? So circle. This is also for your GMAT practice in case they throw an analogy at you. Circle is to sphere, although they don't do analogies on the GMAT as far as I know. As what is it? A ring or a washer is to how the fuck do you? This is going to be botched.
It's fine. We understand what you're saying.
How do you draw a
why
donut?
you doing this?
There you go. I did it. That's a donut, right?
Nice job, Homer.
Thank you. Thank you. All right, so the region of integration we're talking about here is this one. Notice I've only given you the top half of the donut. Do I need the bottom half?
No,
Why not?
because I could just tell that that's what you were getting at.
Yeah, I know. But why? Why did I do that? Why was I getting at that?
Because it's y is greater than 0, it says in the problem.
Right, so we're only looking at the top half of the semicircle, right? All right, when you convert to polar, you got to remember these rules. X equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. There's also, in the same way there was a conversion from Cartesian to spherical coordinates, that rho squared sine phi, there's a conversion from polar, or from Cartesian to polar, and that is dA equals r dr d theta. So when we go to set up this integral, we have the double integral of, what does x squared plus y squared get replaced by?
R squared cosine squared theta plus r squared sine squared theta.
Yeah,
or
but just,
r squared, or just r. No, it's just r. Just r.
well, the square and the square root of the r squared is just r. Yes. Okay, we get r there. Good. What does dA get replaced by?
R dr d theta.
Let's just take this r squared dr d theta. Does that sound okay?
Yeah.
Yeah.
And then what are my bounds on r? So as I draw a ray from the origin, I pierce what circle? The circle of what equation? R equals what?
9.
Nope. That's r squared. Remember the radius would
3.
3, and my outer radius is what?
5.
5.
But would it be 3 to 5 or 0 to 5? Oh, never mind.
It would be 0 if this part was shaded. If there was shading right up against the pole.
Yeah, I see. Never mind. I see.
What are my bounds for theta? So it goes from here and spins around to
0 to pi.
0 to pi. Good. This is r cubed over 3. Plug in 5, plug in 3, find the difference. It's 125 minus 27 over 3, which is 98 over 3. And then you integrate that from 0 to pi, and you get 98 pi over 3. We good on that?
Hold on.
What's 48? Never mind.
What's 48 divided by 3? That's 16. Is that what your answer?
Hmm.
Answer. Whoa.
You having trouble there doing some math, buddy?
No, I got it.
What was your answer? Was it 16 pi?
Hold on. I gotta do 7 theta from 0 to pi.
7 pi.
7 pi. That's not right.
Yay! He's doing it. What are your bounds on r?
3 to 4.
So yours said, okay, so 64 minus 27 is 37.
64 minus 27.
Did you plug in 4 and 3 into your bounds for r?
What's 4 cubed?
64?
No, I'm a dumbass.
What'd you say it was, 16?
No, 48.
Nice job, buddy.
Nice going. Okay, then
Yeah, 48 minus 27 is 21. Divided by 3 is 7.
37 over 3
Pi. Yeah.
pi. 37 over 3. Yes.
Okay.
Got him.
Wow, good job, bud.
Beast mode.
Okay. Yeah.
This kid goes.
4 cubed, 48, beast mode. Okay. Number 6. It's another polar one, but I feel like you need to practice with it, even if it is very similar. In this case, we have the xy plane bounded by x equals the square root of 16 minus y squared and the y-axis. So here's the y-axis. What is this shape? X equals square root of 16 minus y squared.
16 minus y
The
squared.
square root of 16 minus y squared is what shape? Okay. What is the shape of square root of 1 minus x squared? Y equals.
Well, 1 minus x squared is a parabola.
Yeah, I agree, but it's the square root of 1 minus x squared. We talked about this last week. This is the right semicircle of radius 4.
Semicircles.
Yes, this is a semicircle. This is the upper semicircle. If it's negative square root of 1 minus x squared, it's the lower semicircle. And if this was negative square root of 16 minus y squared, it'd be the left semicircle. We're good on that?
Mhm.
Okay, so this is a semicircle. All right, good. We're going to shade this. This is the region of integration. Let's set up our integral. We have double integral of 4e to the something. That something is negative x squared minus y squared. What are we going to replace negative x squared minus y squared with? Or if we're converting to polar?
Negative r squared.
Bingo. And what's our conversion from Cartesian to polar?
Huh?
R d theta.
Thank you, r d theta. We always have to slip in. If we're going to switch from Cartesian to polar, we have to throw in an extra factor of r. So we're going to say 4r e to the negative r squared dr d theta. What are our bounds on r?
Hold on. 0 to 4.
0 to 4? Good. No. Why am I hearing my voice? 0 to 4.
Negative pi over 2 to pi over 2.
Good. Now we just integrate. Now you will have to do use up here. What's my choice for you?
Negative r squared.
Negative r squared. Du would be negative 2r dr.
Wait, what? Oh, yeah.
Mm-hmm.
What I'm going to say here is that we have, what do we have out in front of our e? We have what?
4.
4r. Negative 2r is going to be used up from that 4r so as to be able to allow us to convert from dr to du. So if I divide negative 2r into 4r, what do I get?
Is that R there for you, Logan?
What?
Because I just have 2e to the negative.
Yeah, it's from the dA. It's from the dA. It's from the
Oh,
dA.
my bad.
I was going to say, we could use, I think you're the one who even said, Brandon, r dr d theta, right?
Yeah, it might be. I just didn't see you move that.
Well, yeah, so I mean, I don't know if
He
it's...
did it and then he erased it.
Yeah, I'll just keep going.
Negative 2 and then times e to the negative r squared, or negative, now just e to the u, du. The integral of which is negative 2 e to the u, which when I back substitute gives me negative 2 e to the negative r squared. Plug in 4, plug in 0, find the difference. This gives me negative 2 e to the negative 16 minus negative 2 e to the 0, which just comes out to be, oops, not 1, but 2. Minus 2e to the negative 16. Right? So far, so good. And then I integrate that from negative pi over 2 to pi over 2. But that's just going to, so I'll tell you what that ends up giving me. It just ends up multiplying by a factor of pi at the very end.
Hold on.
Is that good? Like I said, sometimes you will encounter some sort of use up from time to time. You just have to deal with it.
Wait, so you multiplied the 4 by...
What for? Oh, did I forget to do that at the beginning? No, I didn't. Wait, okay, look. Do I have to go over U sub all over again? Do I have to talk about how to do a U sub? Apparently.
Yeah, I'm just confused because my numbers are a little different.
Well, what do I have here?
I have a 2, you have a 4.
Okay, what do I have?
You have a 4.
For what?
4R.
What's my conversion from dr to du?
Negative 2R dr.
So I'm going to take out a factor of negative 2r out of 4r. That will leave me behind with what?
2.
Not just 2. If I took out a factor of negative 2r, I'm going to be left with what?
Negative 2.
Right?
Okay, so I'm going to be left with a negative 1.
Yes.
E to the u.
All right, we're moving on, buddy. Sorry. You got it from there. Logan, did you find your answer?
Yes.
Okay. Brandon, we can do yours this time if you want.
All right, what number are we on?
Well, 7 is identical to number 6 on
8.
Yeah, we'll just do number 8. If you can do 6, you can easily do 7.
All right, 8. I have Integral from 0 to 2. Integral from negative square root 4 minus y squared to,
Yeah. Okay. And then you have x squared, y squared as your.
and I have 2x squared y squared dx dy.
Okay. So 2x squared y squared, negative root 4 minus y squared to positive 4 root minus y squared, negative 2 to 2. Is that right, Brandon?
0 to 2.
0 to 2.
Out of bound 0 to 2.
Okay, let's draw, before we start integrating, let's draw what this region looks like. Because first off, you're not going to want to integrate this as is. So yes, they've given you the order dx, dy, right?
Mm.
Do you want to integrate this as is? Probably not. What's the integral of x squared going to be?
With respect to x,
Yep.
x cubed over 3.
But then I have to plug in square root of 4 minus x, square root of 4 minus y squared. That would be nice if the power on the x was x squared, but the power on the x is now what?
X cubed.
X cubed. It's not going to be pretty, right?
Yeah.
And to be fair, this question does say by converting to polar, but in a real testing like situation, you might not know eventually if this integral, and you might not know to think to switch to polar. But what is it about this? What is it about this shape based on how the bounds are described that is telling me we should probably use polar? How are the bounds being described, or what shapes are these?
Circles.
Semicircles, right?
Semicircles, yeah.
This is which semicircle is this?
That's the left.
Yep, it's a left semicircle, and then followed by the what up top?
Right.
The right semicircle. Now it looks like the full circle, right? We have the left semicircle and the right semicircle together, makes the full circle. What are my bounds on y though? Y goes from where to where?
0 to 2.
So 0 to 2 means which part of that circle do I want?
Top half.
Top half, right? So I just want that, okay? Let's convert this to polar now. So every instance of x gets replaced by r squared. Every instance of y gets replaced, every instance of x gets replaced by r cosine theta. Every instance of y gets replaced by r sine theta. So I end up with 2 r squared cosine squared theta times r squared sine squared theta. And then what's my conversion from Cartesian to polar?
RDR.
Theta.
RD theta. So, and then let's get the bounds. Well, let's actually do the bounds the next line. So we have 2r to the 5th cosine squared theta sine squared theta, d theta. And then what are my bounds based on the picture we've drawn here? As I draw a ray starting at the origin toward the edge, what's my lower bound for r?
Sorry, I'm
Sorry, what?
Looking at the picture here, what's my lower bound for r?
0.
What's my upper bound for r? These are semicircles with what radius?
4.
Try again.
2.
Thank you.
2, yeah.
And what are my bounds on theta?
0 to pi.
0 to pi. So 0 here going all the way around to pi.
Now just solve.
Kind of. It's not as easy as I would hope. This is where it's going to be a pain in the ass. Integrating this with respect to r is going to be 1/3 r to the 6th. Plug in 2, plug in 0, find the difference to get 64 thirds cosine squared theta sine squared theta. At this point, you should probably use Wolfram alpha. But if you don't have Wolfram alpha at your disposal, you have to use the half angle identities for cosine squared to sine squared. So you will have to say something like, no, I wish Martinez, I don't know if Martinez does this, but I wish he would force you guys to know your half angle identities because it would bust your balls and make you know you have to do all your integration stuff. Now, maybe you don't even know your half angle identities. It's not that important in life, but it's a math class, so you should know your half angle identities. You learned them a long time ago. You should know them now. I know them. I learned them a long time ago. The half angle identities for cosine squared and sine squared are, here's cosine, 1/2 plus cosine 2 theta over 2, and then 1/2 minus cosine 2 theta over 2. Those are this is your half angle identity for cosine squared. This is for sine squared. You know what? You're better off just doing Wolfram alpha at this point because trust me, I think you're gonna hate what comes next. So let's just say that.
You're gonna have to learn it at some point.
Maybe. I don't know.
This was 8.
I don't know. She may not put half angle on the test.
That's what I'm thinking. But Dr. Martinez, if you're watching, I hope you roast Brandon and put the half angle formulas on here. Like, burn his ass for thinking, I don't need to study that. Dr. Martinez wouldn't do that to me, would she? If you're watching, do it. Make them know their double angle formulas or half angle formulas, whatever. She's not watching. You're not watching. Number 9. Use spherical coordinates to evaluate the sphere. Blah, blah, blah. Okay. We have e to the integral of, oh, all this giant mess. I guess we didn't need this Jacobian form anymore. Question for you guys. What we talked about moments ago, what x and y and z are for spherical coordinates. I'm not going to write those again, but what is x squared plus y squared plus z squared in polar in spherical coordinates?
Rho?
Yeah, well, kind of. You're warm. What is x squared plus y squared in polar? It's not just r, it's what?
R squared.
R squared. So what's x squared plus y squared plus z squared in spherical coordinates?
Rho squared?
Rho squared. Okay. So with that in mind, I'm just going to go straight to the integral. I have the integral of e to the triple integral, I guess, of rho squared, of the square root of rho squared, which is be rho, times, what's my conversion from Cartesian to spherical?
RD theta.
That's polar.
Oh, I tried.
Rho squared sine phi d rho d theta.
Good job, G.
Yeah. Well done, bud.
Thanks.
Man, this also sucks because you know what? You're going to have to integrate my parts to get this answer.
Yeah.
You're excited, aren't you? I can tell. Let me show you a way in which to make integration by parts a little bit easier on you, or at least I will in a second. I will first actually want to get my bounds on this. What are my bounds for rho? They say W is a solid in it where?
First octant.
First octant. Well, I'm running low on battery, so I hope that we can make it through. First octant, so what are my bounds on rho?
0 to pi over 2.
No. Rho is a measure of the radius of the sphere in question.
0 to 3.
0 to 3.
Yeah, 0 to 3.
Okay. What are your bounds on theta?
0 to pi over 2.
0 to pi over 2 because you're talking about the first octant, so you're going to get the first quadrant. And then what about the bounds on phi?
0 to pi over 2.
Yep, we did this moments ago when I drew the picture of the Earth, right? The first octant, or like the globe, is this. North pole is 0, south pole is pi. I just want this slice here. I just want this guy. Well, that would be theta goes from 0 to pi over 2, just the first quadrant. And then I want the upper part, the upper hemisphere. So that's from 0 down to pi over 2. So those are my bounds on this guy. Let me show you how tabular integration is going to save your life a little bit here. So when you have, I'm going to turn the brightness down so I don't lose this call. When you have something like x to the n times e to the x, and you have to integrate this guy, the integration, the power on x indicates the number of times you have to use integration by parts. So in this case, when I'm going to integrate rho squared times e to the rho, how many times would I have to do integration by parts here?
Twice.
Twice. I don't even like doing integration by parts once. So if I can avoid that doing some sort of technique, I'm going to do that. So here's how this works. What you do is when you have polynomial times exponential, you put
I remember this.
You put the polynomial part here, and you put the exponential part here. Okay?
Yeah, this is fire.
Now, what do you do? Well, if you remember this, what do you do to this column, Brandon?
Derivatives?
Derivatives all the way down until you hit 0. Okay? What do you do to this column?
Integrals?
Integrate. You integrate this column until you're in the same row as the 0. Well, the nice thing about the integral of e to the rho is just that it's what? What's the integral of e to the x? It's e to the x. So the integral of e to the rho is e to the rho,
X.
rho, e to the rho. Good? So, Logan, I don't think you know this because you had Davis, and Davis was useless. What you do when you have polynomial times exponential, and you're
you like draw the lines like downwards.
Yeah. So you do know this, huh? When did we do this?
I'm sure we did this.
Not for Davis.
Beckner, maybe?
Maybe. Okay, so we have plus, minus, plus. You have the alternating sign starting with plus on each of these lines connecting them. So you end up getting rho squared e to the rho, minus 2 rho e to the rho, and then plus 2 e to the rho. And then our bounds are 0 to 3. We're going to plug in 3, plug in 0, find the difference. When I do that, I get 9e cubed minus 6e cubed plus 2e cubed minus what I get when I plug in 0. That's 0 minus 0 plus 2. So I get 5e cubed minus 2 sine phi. When I integrate this with respect to theta and plug in pi over 2, plug in 0, I get pi over 2 times this whole thing. And then I integrate this guy from 0 to pi over 2. This gives me pi over 2, negative pi over 2, 5e to the 3 minus 2 cosine phi.
Wait, where did the 0, 0, and plus 2 come from?
When you plug in your upper bound, you get this. What do you get when you plug in your lower bound?
Oh, you plug in, yeah.
0, 0, and 2. When you catch up to that, by the way, you end up with 5e cubed minus 2 times sine phi. I want to stop for a second and say, if you then integrate that result with respect to theta and plug in pi over 2, you just get pi over 2 times that result.
Say that again?
It's a trick. Ready? Watch. If you have the integral of some function of x with respect, and then I ask you to integrate with respect to y, and I say integrate from 3 to 10, notice the thing I'm integrating is only in terms of what variable?
X.
X. But I'm integrating with respect to what variable?
Pi.
Y. So with that in mind, this whole thing is a constant with respect to y. Or you can say there's no variable y in this function, right?
Mm-hmm.
If you do this integral, I'm going to save you the time. You don't have to say y times f of x, plug in 10, plug in, just say, what's the width of the interval?
7.
So your answer is just 7 times f of x. Okay. Now look at this function here. Does this have any? Now we're integrating with respect to what variable?
Theta.
Theta. Does this have any thetas in it?
Nope.
Nope. So when I integrate it, I end up taking the same function, whatever it is, and multiplying by the width of the interval. What's the width of this interval?
Pi over 2.
So I just multiply pi over 2 and I'm done. Now I'm moving on to the next integral. Make sense? I don't want to have to write theta times 5e cubed minus 2 times sine phi, then I plug in pi over 2, right? I'd rather just say, look, does this function have any thetas in it? Does this function have any thetas in it?
No.
No. So when I integrate it with respect to theta and plug in my bounds, I just end up multiplying by the width of the interval over which I was integrating that variable. That's it. Cool?
Yes.
Okay. Then I integrate that with respect to phi. That gives me negative pi over 2, 5e cubed minus 2 cosine phi. When I plug in pi over 2, I get 0. When I plug in 0, I get 1. But at 0 minus negative 1, so I end up with a plus. I end up with this as my answer. Pi over 2 times 5e cubed minus 2. Is that good?
Yeah.
We've got one last question.
Is that an answer? Yes, that is an answer.
Brandon, we'll do your version. Is it 4x or 4z?
2z dv.
Okay, and this hemisphere is what radius?
1. It's 1.
Over the whole hemisphere. Okay, cool. We're going to convert this to spherical. Duh. What is z in spherical coordinates? I'll tell you what. Whoever can tell me the conversion from Cartesian to spherical doesn't have to tell me what z is in spherical.
Wait, what?
One of you is going to do one of these. The other one's going to do the other. Whoever does this one, the easier one, doesn't have to do this one. What's the conversion from Cartesian to spherical?
Rho squared sine theta d rho d theta d phi.
Sine phi.
I think Brandon gets it because you were close, but you said the wrong thing, Logan. It's sine phi d rho d phi d theta.
I said phi.
No, you said theta, brother.
You said theta here, buddy.
That's fucking horseshit.
Now, with that in mind, Logan, you've got to come up with what z is in spherical coordinates.
No way. I gave that man.
This is recording, Logan.
He doesn't care. All right.
It's ridiculous.
This is rho cosine phi. You have to know this.
Might have to censor this recording, Andy.
Yeah, you're gonna have to.
People on YouTube will live. I'll make sure to put the check mark that says this is not for kids. Okay. What are my bounds on rho?
Nothing.
0 to
0, 2.
1.
Yeah, 0 to 1. So radius 1 hemisphere, right? Yes, Brandon, do you have the radius 1 hemisphere?
Yes.
Okay. What are your bounds on theta?
0 to pi.
No.
Or
I'm going to go all the way around.
0 to 2 pi.
2 pi.
2 pi. What are the bounds on phi?
0 to pi.
Nope.
I can't tell in your drawing. 0 to
Do I want the whole globe or just
0 to pi over 2?
0 to pi over 2? If I want the whole globe, I say 0 to pi. If I want the top, everything from the North Pole down to the South Pole, I'd say 0 to pi. But in this case, I want everything from the North Pole to the equator, right?
Yeah.
But that might say 0 to pi over 2. I want to multiply this out. This is going to give me 2 rho cubed sine phi cosine phi. And when I integrate this guy with respect to rho, I get rho to the 4th over 2. Plug in 1, plug in 0, find the difference. When I do so, I get 1/2 sine phi cosine phi. Now I have to integrate that with respect to phi. The integral of 1/2 sine phi cosine phi. By the way, you can use a half angle identity. So we just, or a double angle identity rather. I just talked to you about what that sine 2 phi equals 2 sine phi cosine phi. So if sine 2 phi is 2 sine phi cosine phi, what's half sine phi cosine phi? Well, that'd be sine 2 phi over 4. Or you can do a u sub. What's your choice for u here?
Sine phi.
Because du would be what?
Du would be cosine phi.
Cosine phi, what? Whole thing, cosine phi.
D phi.
Right, so this would be what?
U.
And this whole thing would be what?
U cosine squared.
What the fuck?
Wait, what? What are you saying?
You just told me that u is cosine, or you just told me that u is sine phi. So what's du?
Cosine.
Cosine what?
Phi.
Cosine phi.
D phi.
Okay, so this would be what?
U.
And this would be what?
Du.
There you go. That's what I'm trying to say. Not cosine squared. What is that? So when you end up doing this integral, you get 1/4 sine squared phi. Plug in pi over 2, plug in 0, find the difference. When you do that, I get, this is for phi. I opt to integrate first with respect to phi instead of theta, but whatever. This is going to give me 1/4. Now what's the integral of 1/4 with respect to theta from 0 to 2 pi? Let's use the trick we did before. Does this integral have the variable we're integrating over in it?
No.
No. So I just need to multiply this result by the width of the interval. What's the width of the interval?
2 pi.
Times 1/4 would be what?
Pi.
That's your answer. Okay, my battery's super close to dying. Are there any other questions on this?
No.
I probably potentially will do an exam review if people who are in GroupMe drum up enough interest. If you just at me, at Easy A, hey, will you do an exam review for this class because we need it and we're bad at math or whatever. Say whatever you want in there. Just make sure you at me because I'm not going to do it unless there's enough people that want to actually participate in an exam review. Cool.
Yes, sir.
Cool. And when is that exam one more time? It's the 14th.
A week from tomorrow.
Week from tomorrow. Okay, I'll probably do something like a weekend exam review, maybe a Monday or a Friday exam review.
Alrighty.
All right, cool. All right, guys. Any parting words? Any parting words for the video?
Thanks, Andy. I love you.
Love you too, buddy. Bye.
Bye.